Good morning, everybody. I hope you're all doing great. This is a screencast to help with section 5.3, which is about the shapes of molecules. So I will just go through these slides that are posted on Schoology, and hopefully it'll make some sense for you. All right, so the basic idea is that if we have drawn a Lewis-Dot structure, that is a flat piece of paper, it's a two-dimensional structure, and we want a way to predict what shape that will take in real life, or in space. Okay, so there's a few things that play into that, which the first one is that bonds are going to repel each other. Bonds are made up of electrons. Electrons are negatively charged. Like things repel, opposite things attract. So the electrons in a bond want to push away from each other so that they're as far away from each other as possible. So the PhET simulation that some of you may have looked at kind of shows that. So let me just demonstrate this for a second. So here's that PhET. So this is the starting page. If I drag an atom in there, and I've made one bond to that central atom, and I drag another one in there, it automatically goes as far apart as it possibly can, because that bond is made up of electrons, and so is that one. And they don't want to be near each other at all. So if I try to drag one of them closer to the other one, I can't even do it, because they just push away from each other until they can get as far away from each other as possible. That is what this is all about. All right. And if I drag in another atom and bond it to that central atom, same thing happens. Look, I can't even pull them any closer to each other. It's impossible, because those electrons just keep pushing each other away. All right. So that's what this means. Molecules arrange themselves in 3 dimensions so that bonds are as far apart as possible. All right, that is called VSEPR theory. Okay, this is just the theory that allows us to predict the shape that these things are going to take. And we're going to use our Lewis-Dot structures to predict the shapes. All right, and it stands for valence shell electron pair repulsion. So the valence electrons are all in the outermost shell. If you think back to the Bohr model, the outermost shell is the valence shell. That is where these electrons are that we care about, the ones involved in bonding, and they push away from each other. So that's all that means. All right, it's a big fancy abbreviation, but it's very simple. All right, so one thing that's very important for you to understand is this new word called electron domain. And all that means, the word domain means, an area or where something lives. My domain is my house. The electron's domain in a bond is where those electrons are located. So if I look back over here, that bond contains electrons, so that's an electron domain. That is an electron domain, and that is an electron domain. So in this particular example, there are 3 electron domains. Single bonds count as 1 electron domain. So in this case, there are 3 electron domains. If I took away one of those bonds, let me start over, and I just added 2, now I have 2 electron domains. Okay, because I have 2 single bonds. If I added a double bond in here, that double bond is 1 domain, because in that region, there are electrons. There's 4 electrons, but they're all in the same area, the same region, or the same domain. So that double bond counts as 1 electron domain. That single bond counts as 1 electron domain, and that single bond counts as 1 electron domain. So in this example, there are 3 electron domains. Okay, a double bond is 1 electron domain. A triple bond is 1 electron domain. Let's put a triple bond on here if I can. All right, so now that triple bond, all 6 electrons in that triple bond are in that one location, so they count as 1 electron domain. The double bond is 1 electron domain, and those single bonds are each 1 electron domain. So in this example, there are 1, 2, 3, 4 electron domains. So that's something you're going to have to know how to do, is count electron domains. So let me take all those off again. All right, let's try this again. There's a double bond. There's a single bond. How many electron domains are there? I hope in your head you're answering 2. 1, 2. Okay, another thing is that a lone pair also contains electrons. It's not bonded. They're a non-bonding pair. So if I dragged a lone pair on there, that is also an electron domain because that's a region where there are electrons. So in this picture, I have one electron domain, I have another electron domain, and I have another electron domain. Okay, so that's really one thing you have to be able to do is figure out how many electron domains a molecule contains. All right, so that's one important idea. And then we're going to use our handout that hopefully you picked up from the cart in the hall with all these shapes on there. Okay, and it looks like this. It's green and it's called molecular shapes. And we are going to use this handout and this chart to predict the shapes. Here's some of the shape names: linear, trigonal planar, bent, tetrahedral, trigonal pyramidal, and then there's another one called bent. Okay, so this green handout, super, super handy. All right, I have it right here. I have my camera on and I have my copy of the handout. I don't know if you can see that actually. So let me go back to where I was. All right, so here's what we're gonna do, okay? This is how you use this handout. If you have drawn a Lewis dot structure with a central atom and 2 bonds to it, the shape of that is linear. So if you look over here on your handout, right, 2 electron domains, we don't have any lone pairs, that shape is called linear. All right, if you have a Lewis dot structure with a central atom and 3 single bonds going to it and no lone pairs, you look at your chart, I have 3 electron domains, I have no lone pairs, the shape of that is called trigonal planar. All right, and you can just go right on through here and figure out these names. 4 atoms, no lone pairs, tetrahedral, that's this one, 4 atoms, 4 bonds, 4 electron domains, no lone pairs, tetrahedral. So let me show you these on this PhET thing. Okay, I'm going to switch this to real molecules. And I'm going to say, show me water. All right, there's water. I know that you know how to draw the Lewis dot structure of water, but there's 2 bonds and 2 lone pairs. So the name of that is bent. And if you looked on your chart and you had number of bonding domains, number of lone pairs, water's got 2 bonds and 2 lone pairs. The name of that shape is bent. Okay, let's do another one. Let's do ammonia. All right, here's NH3, ammonia. All right, so I can drag it around. My nitrogen is in the middle, and I have 3 H's, HHH, and a lone pair. So I have got, it's kind of hard to see that back one. Oh, there it is. I have 1, 2, 3 bonds, and I have 1 lone pair. The name of that is trigonal pyramidal. And if you look on your chart, all right, I have 3 bonds. I have 1 lone pair. The name of that shape is trigonal pyramidal. All right, I'm going to do one more for you. All right, CH4. Okay, so here is CH4. My C is in the middle. And I have 1, 2, 3, 4 H's. I have 4 single bonds going to that central atom. And the name of that is tetrahedral. Okay, and if you look on your charts, I have 4 bonds, no lone pairs. That shape is called tetrahedral. Okay, so you can use this PhET to kind of figure this out. The link is on Schoology. But the thing to do is to just kind of go through these slides and try to figure out the shapes. And these are the ones that we just did. And hopefully that helped. And we will, of course, practice this some more. And That's it. Thank you very much.